In this episode, we will discuss those threats to human existence that have extraterrestrial origins, what we call cosmic threats. This includes things like supernovas, magnetars, exploding galaxies, coronal mass ejections, and meteor strikes by asteroids or cometary objects. We have a separate episode entirely devoted to natural threats originating from the Earth itself. Both of these episodes can be considered as risks posed by quote-unquote Mother Nature, meaning that humans are not the primary causal factor. Here we see a detailed three-dimensional animated depiction of a supernova. Supernovas occur when a sun explodes, radiating an enormous amount of energy. They are fairly rare events, happening about only twice per century in any galaxy. These events are often visible from Earth and so become part of recorded history. Based on such records, we know that 4 supernovas at least have been observed. Some of these events were so energetic that they cast shadows at night and were visible in the daylight sky. Another important aspect of supernovas is the type of radiation that they emit. The most dangerous of these are gamma rays, which can degrade the ozone layer. How perilous this is for us depends on the distance. If one went off sufficiently close, say 30 light years from Earth, it could strip away the ozone layer, exposing our planet to deadly radiation from our own sun. This would most certainly result in a mass extinction event. The likelihood of a gamma ray burst is once every 240 million years. However, astronomers report there are no stars this close to us that are likely to go nova anytime soon. Despite this, there is a long-term risk. We know based on the presence of iron isotopes that the Earth and Moon have been subject to the ejecta of supernovas from just a few million years ago. One way to form a neutron star is from the collapsed remnant of an exploded star. Neutrons are so dense that a single tablespoon would weigh more than Mount Everest. A magnetar is an exotic type of neutron star, one with a very powerful magnetic field. In 2004, a flare on the surface of a magnetar compressed the Earth's magnetic field from a distance of 50,000 light years away. All this from an object that's estimated to be only 15 miles across. Do these strange denizens of the universe pose a threat to Earth? Magnetars can periodically send large bursts of gamma radiation and what are called fast radio bursts, or FRBs. The closest magnetar to Earth is only 9,000 light-years away in the constellation Carina. Recent research shows that unstable magnetic fields in one of these stellar remnants can crack open the crust, creating flares which would emit fast-moving gamma radiation. If one of these were to hit our planet, it could definitely cause trouble. Here we see a video of a magnetar formed from the collision of two neutron stars. Supermassive black holes are at the center of most galaxies. These suck everything nearby into them and in the process can emit enormous amounts of energy. What happens here is still somewhat mysterious. Astronomers have witnessed a gigantic explosion in galaxy M82, otherwise known as Ursa Major A. Physical debris was detected traveling outwards from its center at 3% of the speed of light. In terms of the infrared light spectrum, which corresponds to heat, this explosion was the brightest thing in the observable universe. It may be that this event was triggered by the adjacent galaxy M81, since the two are spiraling in towards each other. These phenomena have since been dubbed starburst galaxies. Needless to say, if our own or even a nearby galaxy exploded, it would emit all sorts of dangerous radiation and fast-moving material that could pose a fatal or serious hazard to Earth. Solar flares occur when our or another similar type of sun sends out a surge of electromagnetic radiation. The occurrence of a solar flare varies with the 11-year solar cycle. One event that is associated with such flares is an even larger ejection of plasma and magnetic field called a coronal mass ejection, or CME. A CME can travel through space in directions where they don't impact Earth. Others can hit the Earth where they interact with our own magnetic field, causing various types of disruptions. Here we see a video of a coronal mass ejection. In 1859, a CME known as the Carrington event damaged part of the newly formed U.S. telegraph system and started fires. If a similar event happened today, it would cause much wider destruction, an estimated $1 to $2 trillion in the first year alone. It would damage electrical transformers, destroy radio communication, knock out satellites, affect the GPS system, and even pose a threat to airlines in flight. Our current systems aren't yet hardened against this type of event, but we can at least see it coming. There are a set of satellites in orbit that measure the sun's activity and can provide us with 2 to 4 days of warning time. We are almost certain to see this type of event within a century or so. It thus poses a significant near-term threat, but one that we can prepare for. Asteroids are small rocky objects that orbit the sun. They are much smaller than planets. There are thousands of them in our solar system. Many pose no direct threat to our planet. Some, however, have orbits that can put them on a collision course for Earth. If an asteroid or a comet, which are typically made up of dust and ice, enters the Earth's atmosphere, they are called meteors. When these objects are small, they can burn up in the atmosphere and nothing really happens. If not, however, they can strike with great speed and cause horrific extinction-level events. The most famous meteor of all is the one that killed the dinosaurs 65 million years ago. It was 6 miles across and struck in the eastern Yucatan Peninsula of Mexico, forming a crater 110 miles wide and 12 miles deep. It threw up large amounts of debris into the atmosphere, blocking out the sun and causing plant life to die out due to lower temperatures and lower levels of sunshine. Here we see the terrifying result of what a large asteroid impacting the Earth might be like. The Center for Near-Earth Object Studies at the Jet Propulsion Laboratory in Pasadena, California, calculates the orbits of all near-Earth objects and makes an assessment of their potential risk. It does this in coordination with NASA's Planetary Defense Coordination Office. Fortunately, most of these objects won't get anywhere near our planet. Those defined as potentially hazardous are larger than 500 feet across and get within 4.6 million miles of Earth. There is no significant threat of a major impact for the next 100 years or so. Here is a quick summary of how we might spot a near-Earth object that could potentially be a threat.
How do we spot near-Earth asteroids? To start, survey telescopes scan the sky. When multiple pictures of the same spot show a speck that's moving, computers automatically check it against a database of known objects. If there's no match, it gets added to a list of objects to confirm. And if it looks like it'll pass very close to us, we give it top priority. Then it's time to call in reinforcements. More astronomers from NASA, other institutions, and even the amateur community submit additional observations. Each new data point helps refine the projected path, and this asteroid is going to fly right on by. All the info will be posted online, so it can continue to be tracked and monitored. Nice work, Planetary Defense Team. Keep watching the skies.
Okay, so let's summarize. On the bright side, many of these threats are low risk, but also predictable. We can anticipate when a star might explode because we understand stellar evolution fairly well. We are also able to map the orbits of near-Earth objects in detail and may even be able to nudge some of them out of the way in time. So, although the universe is a dangerous place, the key to our long-term survival is understanding how it operates and then using technology to mitigate the risk.